So hello everyone. My name is Eli Dart. I work for ESNet at the Berkeley National Lab. My role here today is presenting as a member of the CMB S4 collaboration. And I will say at the outset that Simone did a much better job than I'm going to. And he had a whole bunch of really nice detail in his talk. And you know, as he mentioned, S4 and Simons are collaborating well because there's going to be some common infrastructure use between the two projects. So that's all been going really well. So I'm glad I'm following Simone's talk because he gave a bunch of really good information already. So this presentation includes lots of work by people who are much smarter than me. I'm not actually a real scientist. I just help them. And so I'll do my best to present the science portions of this. But if you ask me any questions about it, I'm probably going to have to refer you to somebody who's actually an astronomer because I'm not. So again, but thank you for the opportunity to present CMBS4 today and to give an update sort of on where we are. So what is CMBS4? It's the 4th generation ground-based cosmic microwave background experiment. And so we're sort of following in the footsteps, right? As Simone mentioned, right? There have been a bunch of precursor and experiments and previous work, and so S4 is stage 4 to follow on after those things, and where at least one of the intents here is to sort of bring some of the of DOE's infrastructure into and to complement the existing NSF funded program. So this is a joint DOE and NSF project. From a DOE perspective, it's in the high energy physics office, but we're going to scale up to quite large. I mean, many petabytes of data, and we hope to make the full scope of that available to the entire scientific community. So a little bit about history just of this project, right? This goes back a number of years, but it was recommended in P5 after the community converged around it in Snowmass first. We've been holding workshops biannually, but then this has been the community has really come together behind this as sort of the next big project in this space, and so there's a bunch of things all coming together, and we're hoping to move it all forward. So there's a set of science goals here. Again, I am not an excellent astronomer, and so there's a bunch of stuff here that I don't really understand. I wish Julian were here to give this talk, because he would do a much better job of explaining the science than me. Here's the approximate construction timeline and operations timeline for context. This is a pre-COVID plan, and as everyone knows, COVID has not been kind to schedules, and so there's a little bit of shifting around that has happened here, but everyone's trying the best that they can. So where are we going to put this stuff? If you look around on planet Earth, there are only really a few sites that are good for this sort of thing. The CMB community has a long history of working both at the South Pole and in Chile. And so these are the two sites that CMBS4 is actually going to deploy at, both Chile and the South Pole. So it's great that we have the two sites. So Chile can go wide and the South Pole can go deep. So that's the current plan. I think the telescopes are set up with that in mind. So some large aperture telescopes, some in each location, and then the SATs will be at the South Pole. I guess it's possible to relocate those to Chile. You'd have to talk to Julian more about that. I mean, some of the detector numbers here are just amazing, right? So, 500,000 sensors, et cetera, et cetera, et cetera. It's a really cool project. I'm actually really glad to be supporting this. And so, by the time you look at all the detectors and the observation timeline, right, the number of detector years is in the millions. So it's great. So timeline, we're hoping for operations 2029, 2030, something like that. Again, COVID has caused some scheduling problems, but we will do as best we can. This is a schematic of what we expect to do in terms of data management, right? So there's if you imagine two bands going through this, right? The upper band is on the Chile side, and the lower band is on the South Pole side. So for Chile, it's going to come. I'll get into this in a little bit. Simone talked about the fiber build up to Cerro Toco. So we're working with our Simons Observatory colleagues in the hopes of being able to use that infrastructure. That then comes down through Reuna, through AmLight, through ESNet to NERSC, which is the primary data storage facility. And then the backup data storage facility is at Argonne, so the data will be replicated there. And then in those computing environments, there will be a whole bunch of computing work that gets done to generate a set of data products, and then those data products will be made available to the community. For the South Pole, it's nowhere near as nice, and we're so what was being discussed earlier about a couple of folks have mentioned SneakerNet, and it's like, yeah, well, disk packs on planes is kind of what we're stuck with for a large scale data movement off the South Pole. I mean, there's some small amounts of data that will come across TDRS on a continual basis or a daily basis, but in terms of larger scale data transfer for larger scale data analysis, that's going to happen with physical transport of photo media. So in terms of networking in Chile, then the data rate that we're expecting it's over a gig, so we're going to need to provision for 10, and especially because in the event of an outage, there's going to be some catch-up time. So we've got a big disk buffer, or there will be a big disk buffer up on the mountain to collect the data in the event that NERSC is unreachable for some period of time. But then, it shouldn't take us very long to clear that backlog when the network comes back up, provided we have 10 gig provisioned there. And there's some exploration too with Fabric for seeing if some aspects of transient analysis can be done using Fabric sort of in transit. So I think it's Don Petrovic is working with the Fabric folks on what that might look like. But as I mentioned already, we're in close collaboration with Simons, working with Simone and others, and that's been a really good collaboration. So thanks to the Reuna folks for letting me use this picture to illustrate where we're going to end up so there's going to be a fiber that goes up the left-hand side there, up onto the Cerro Toco, and that'll come back down to the Reunipop at ALMA, which has already been described in the context of several other experiments today. So we're collaborating with Simons and collaborating with Reuna on exactly how all this is going to get done, but it's moving forward, which is great. So something that's, I think, new since last year is we've done some prototyping on data distribution from the computing center. So we're making use of the Modern Research Data Portal design pattern, which is something where you can take your normal web-based portal that you might use to search for or discover or select data sets. And then on the back end, it's hooked up to Globus so that if you have to move large amounts of data, the human doesn't have to do extra work in terms of data set selection or things like that, right? It just pops up a Globus job and away you go. So we have a prototype data portal up now, and we're using this as a data distribution service for the data that's coming out of Data Challenge 1. So there've been a bunch of simulation runs and so on that have already generated a bunch of data. I think they're still in the process of processing it, though. I don't think it's actually been published. There's some data there in the portal, but not as much as there will be in the future. So here's some screenshots of what the portal looks like, right? So here you are, and if you're able to log in there, then you can see there's these different data sets here and so on. And if you select them and click transfer, it'll generate a Globus job for you. And you select the destination endpoint, push go, and away you go. It's similar to to what's been deployed in other communities. So like the Research Data Archive at NCAR has this. There are several others. I think DESI might have one. Anyway, there are several of these in the community now. So this is what we're doing, at least at the moment, to try this out and see if it works for distributing the larger data products out to the community. And so then what's the back end look like? It turns out it depends on what endpoint you use. So this is for the replication then between NERSC and Argonne. And if you just do bulk replication, it runs it over 8 gigabytes a second. So it cooks along pretty good. For the data portal itself, it uses a different endpoint, which NERSC doesn't have as many servers provisioned for, and so that runs it at around 1 gigabyte a second rather than 8 gigabytes a second. But it's just a question of how many DTNs you put behind the thing as to how fast it goes. So it's working pretty good for us for now, and we're again experimenting with this to see whether this works for the project going forward. I think that was my last slide. So I will stop there and I will take any questions that anyone might have. Thanks.
Eli, I have a question for you.
Yeah, sure.
So I think I saw in one of your slides, in your diagram, you had Exceed and Open Science Grid.
Probably so.
Just wanted to get an understanding of their roles with S4, how that's gonna.
So I don't know for sure. So as far as I'm aware, it's not sort of in what I would call the data acquisition pipeline, or this sort of primary data production pipeline for S4. Now, if you scientists are going to work on your next Nobel using this data and you want to do it on OSG, presumably you could transfer it to an OSG resource. And I think part of the data distribution task in this project is to make it easy to get whatever data a scientist would need, make it easy for them to move that to a place where they can compute on it, right, if they're not able to use one of the pre-computed data products, or just run their code at NERSC in the environment there. Because I think there's an expectation in this project that a lot of the scientists are actually going to do their work using NERSC computer resources. And so at that point, then the data is co-located with it already. You don't have to move it anywhere, and that's great. But then if someone has a need to move it someplace else, of course, we want to facilitate that and be able to do so in a way that doesn't come with a large human cost, just to get the data where it needs to be in order for someone to be productive.
Okay, that makes sense. All right, thank you.
Thanks.
Bob, you have a question?
Yes, I wasn't sure I was unmuted. Thanks, Eli. Could you say a few words about what Fabric is and how you do alert processing in transit?
So Fabric is a high-speed testbed funded by NSF. I don't know a ton about it. It's in the process of being built, actually. And so there are a couple of things that the Fabric folks are trying to do. And one is sort of in-network services or capabilities, right? And so if you say were to attach some amount of computing and storage directly to the network and come up and have a way for a science project to pass data through whatever that computing capability was, maybe you could do some event detection or feature detection or something in real time or quasi real time. And so, this is not, I think, a fully deployed capability yet, but it is certainly something that folks are looking at. If you have interest in, do you know Don Petrovic?
Mhm.
Yeah. Okay. So he's the person who. Oh yeah, I guess he used to have a role in LSST, so of course you would know him. So I'm pretty sure he's doing transients for S4. And I'm pretty sure he's been leading the interface with Fabric. Sorry, I can't tell you more. I'm not part of the team that's doing the details of that.
Yeah, no worries.
Bob, let me comment on that as well. There are some Vera Rubin folks working with the Fabric team. Will O'Mullane is one, and I forget the name of the lady who is a scientist there at Vera Rubin. I forget her name.
Probably Leanne or Yusra.
It's Leanne Guy. So they are working with the with the Fabric team on providing them with data movement requirements. They had a recent meeting. I participated. So you could probably get quite a bit of information from Will.
Okay, thanks.
Yeah.
Excellent. Thank you, Julio.
Mm-hmm.
Other questions?
All right.
Okay.
Eli, thank you so much.
You bet. Back to you.
That was a great talk. I think you'll make a great astronomer one of these days.
I would have to go back to school for a long time. But
You'll be fine. Yeah.
Equivalent
All right.
experience is accepted.
Okay, so our next speaker is for Meerkat, Bradley Frank.
Yeah, hi. Hi, everyone. Let me just share my screen quickly.
All right, great.
Hi, thanks. Is that full screen?
Yes, now it is.
Okay, great. So I just wanted to thank the organizers for inviting me to give this talk on Meerkat. So I give this talk on behalf of my colleagues at the South African Radio Astronomy Observatory, in particular our chief scientist, Fernando Camillo, and one of my very close colleagues, Simon Ratcliffe. So, given that this is my first appearance at this workshop at this forum, it wasn't too clear about exactly what kind of information would be relevant. So I tried to jam as much as possible, with the understanding that some of the more intensive information about our network infrastructure will be covered tomorrow. So if you don't already know, the Meerkats Telescope was initially conceived as an SKA pathfinder. So Meerkat literally stands for More Karoo Array Telescope. Meer is the Afrikaans word for more, and it operates as a radio interferometer. So it, at the moment, comprises 64 13.5 meter dishes with a maximum physical baseline of about 8 kilometers, which gives us at L-band a resolution that is, better than about 10 arc seconds. We currently operate at L-band, which is about 900 to 1670 megahertz, and at UHF 580 to 1015, and a full polarization, a full band, and a full synthesis observation generates about 24 terabytes of data. So thanks to a presentation that happened earlier, I don't have to explain exactly how synthesis happens, but we achieve a full synthesis in about 8 hours. So for a full polarization 32K observation, we generate about 3 terabytes per hour. And so our current operations, so we're currently involved in science operations, and our science operations is split between a lot of time spent on our large science projects, which are the LSPs, and open time projects as well. So that's our current operational model. From this year moving forward, what we can look forward to is the commissioning of the S-band receivers, which are at a higher frequency, and the construction and integration of Meerkat Plus. So Meerkat will then include 16 SKA1 mid dishes. So this is just basically a brief history. So in 2003, our SKA South Africa project office is established. In 2006, we built our first dish using an experimental methodology. In 2009, before the construction began, we issued out a call for Meerkat science proposals. In 2010, we had our successful concept design review. Skip ahead a few years, in 2012, SKA announced a split site decision with us hosting the mid frequency array and Australia hosting the low frequency array. 2014, we saw our first Meerkat dish. 2015, we had our receivers on. And in 2018, our telescope was formally inaugurated with our fantastic image of the Galactic Center. So this is quite a nice map that was created by one of the users of what the Meerkat complex looks like. So each of the orange dots is a dish, and with the maximum baseline between M59 and I think it's MO3 is about 8 kilometers. So in this image, I think it's important to note that we have our Karoo array processor building is well further to the south. It's hidden away from the telescope and built into the mountain, and that's where our correlator actually lives. And our operational center is also co-located as well. So this is what it looks like in the Karoo itself. So this is on the top left, you can see the dense core of our telescopes. If you're standing in the middle and you're looking out and through one of the support structures, that's what you see in the middle. We have our assembly building, which is actually on site as well. So we assemble the dishes and we roll them out onto site. We have one of the biggest cherry pickers in Africa, which helps us hoist the dish structure into the pedestal. And on the bottom right is a picture of the Karoo array processor building. So you see that this is in a bunker, and that's where our correlator lives as well. In terms of our science program, so as I mentioned before, in 2010, we had a call for scientific proposals, and this resulted in 10 large survey projects. And this is one of the first telescopes of the modern paradigm that had already dedicated a substantial amount of time to large surveys, and very much mimicked and was meant to pathfind the sort of operations that the SKA will eventually embark on. So in 2016, Meerkat is indeed a different telescope than planned in 2009. In 2009, we had initially planned to have 80 dishes. that were 12 meters each. In 2016, we ended up with 64 offset Gregorian dishes, which actually have a better filling factor and a better operational efficiency. These proposals, the survey proposals, were thus reviewed in 2017. Our telescope became operational in 2018. And about 2/3 of our time is devoted to the LSPs. 5%, as mentioned, is devoted to DDTs. And we've just recently issued our third call for open time proposals. So all of these projects are underway. And 50% of our time, which is also balanced with maintenance time, etc., but 50% of this time is used for science. We do imaging in a variety of modes in our correlator. So the 4K mode is 4,096 channels that are distributed over the 856 megahertz bandwidth. And that is the so-called wideband mode, although you can detect line emission in those channels. The narrowband mode, which is by far the most sort of avant-garde mode, I would say, is 32K channels across 107 megahertz, which gives you really, really high frequency resolution. We also do pulsar timing. And so thus far, we've had about 1,000 pulses that have been observed. We have commensal users as well. So the idea is that there are optical surveys that are observing at the same time, obviously at nighttime, in the same patch of sky that Meerkat is pointed at, with the express aim of looking at transients. So essentially, the Meerkats Telescope, for example, is always observing at the same patch of sky that Meerkat is. Recently, we've also started observing with the UHF band. S-band, as I mentioned, is still being commissioned. At the moment, we are oversubscribed, and many data sets are no longer proprietary. So the visibilities and many of the images are also available through our archive interface. So if your colleagues are interested in looking at some of the Meerkat data, I would urge you to go to our archive and to search for it and to download data. And so this is one of on the top right panel is one of our most recent the results generated with Meerkat, which is the observations with the narrowband narrowband data of a nearby galaxy, imaged at different robustnesses, which unveils different types of structure. So for this galaxy in particular, it's a case that you would want to process your data multiple times, even though you calibrate it once. In terms of the S-band status, so this is our S-band receiver, and you can see that there's a logo of the MPI, the MPI logos on that receiver. So 64 receivers have been installed, and so the receivers sit on top of this turret that is pointed at the secondary, and the commissioning is currently underway. So we expect to have S-band operating towards I guess towards the end of 2022, and hopefully beginning of 2023, we'll start doing survey work with the S-band receiver. We have also started testing the SKA mid hardware. So this is a picture of the SKA mid telescope, and so some of the band 2 dipoles and receiver machinery is being constructed and tested on site. And so the roadmap for us now is to eventually move towards integration of these dishes into Meerkat to eventually become Meerkat Plus, and the Meerkat Plus will eventually be integrated into the SKA phase 1. So this is essentially just what the rollout plan looks like. So we are at the moment running in an NA64 dish phase. The correlator at the moment is built for 64 inputs, full polarization. And for us to scale out to an 80 input modality is going to require quite a dramatic upgrade to our correlator hardware, and actually to our imaging hardware as well. So essentially, we are trying to take the opportunity to leverage off the advances in technology to actually upgrade our backend, our imaging correlator backend, to take into account new Meerkat Plus phase of operations. In terms of the data flow, so our in the Karoo we have our correlator, and we also have our imaging node. So essentially, the calibration and imaging computing that we had on site was mostly focused on doing quality assurance imaging. What we have found more recently is that the calibration and imaging is sufficiently high quality for it to be useful for science purposes. And so we're currently involved in a phase of work which is trying to compare the outputs of our real-time imager to sort of offline, off-site imaging that radio astronomers typically want to do with software packages like CASA. And the idea is that this will save a tremendously huge amount of time. Cross-calibration and self-calibration is certainly some of the most time-consuming bottlenecks of the entire imaging process. If we can remove the need for calibration and just produce a calibrated set of visibilities for our users to image for their science programs, that would be a win, basically. So the data is then transmitted over fiber to our archive in Cape Town, and then from Cape Town, from the CHPC, the Center for High Performance Computing, the data is made available to third parties. And so this is, I guess, third-party research computing partnerships. So the data is transported over to the observatory. Then we have a data transfer node that's sitting at the CHPC, that is physically located at the CHPC. We have a DTN, a data transfer node, that's also sitting at one of our local cloud-based centers. And we use Globus to mediate these transfers. So essentially, a user comes along, makes a request, presses a button, and the data set is preconditioned, peeled off the raw format, put into a measurement set, and moved over the network to the third-party facility. So the landscape is as follows. We have the Karoo array processor, which does our correlation and imaging. We have the Center for High Performance Computing, which is in Cape Town. That's where our archive is, and that's where we do some of our science computing. And then we also have a partnership with the Inter-University Institute for Data Intensive Astronomy. That's at Cape Town. That is a university-based institution. And that's where a lot of the science is actually generated. So that we are able to benefit off the SANREN, our local research network backbone, so we can transport the raw measurement set data as quickly as possible. We host 5 LSPs and 70% of the South African-based OpenTime projects. We have about 100 nodes that are running OpenStack, and we split that between a majority of Slurm-based compute and Jupyter for highly interactive operations. And we serve about 4 petabytes of raw storage at the moment, which is by and large mostly Meerkat data. So some science highlights. This is our first Nature paper, which really highlighted the how amazing Meerkat is as an imaging instrument. So we pointed it basically at the brightest sort of feature in the southern sky, and made this tremendously detailed image of the galactic center. This is the most sensitive radio image that has been made to date. We reach a sensitivity of almost 500 nanojanskis per beam. This is a project that we did with Bill Cotton from the NRAO. So we spotted in some of our OpenTime data this huge X-shaped galaxy that is indicative of hydrodynamic backflow. As the jets start to hit the interstellar medium, there's backflow or synchrotron emission that starts to create and lead to this morphology. And this is an enormous structure. So radio galaxies is part of our bread and butter, essentially. And this is a very interesting early science result from one of our large science projects, our large survey projects, This is an image of Fornax A. So this is an A-team source, one of the brightest sources that you can find in the radio sky. So it's kind of brave to actually point your telescope towards it and image it. But when you do, and if you spend enough time and have enough computing available, you can produce an image that is as detailed as this is. And so overlaid in the blue are the H1 clouds that reside in this particular system. And so this is much deeper than what was previously done with Fornax A observations, with ATCA, for example. And so we have gone an order of magnitude deeper and unveiled a lot more hydrogen than was previously observed from the surveys. And this is from an example of a science result that I mentioned earlier. This is a high resolution imaging of a nearby galaxy. And this is really one of the science cases that Meerkat was built for. So this is high resolution, highly channelized data imaged at different resolutions used to produce both total intensity data and velocity fields as well. And this is possible with Meerkat because of that excellent angular resolution, but also because of our high velocity resolution as well. We've also found transients with the data. So this is a recent paper that was produced by one of the other Meerkat large survey projects. And so this is observations of a transient with Meerkat at the top and corresponding X-ray observations at the bottom showing a correspondence between a transient event at different wavelengths. We've also done very high precision pulsar timing. So I'm not a pulsar astronomer, but I'm told that 4 nanosecond timing in 1 hour is, well, that is an amazing dynamic range, which we'll be able to achieve with our pulsar timing with Meertime, who is also another large survey project. And we are also running in addition to our large survey projects and our open time projects, we have observed a few so-called legacy surveys as well. And this is an example of a galaxy cluster legacy survey. So these are legacy surveys. We have 3 legacy surveys that are being done with Meerkat as part of the observatories program. Eventually, this data will be provided to the public. Galaxy clusters is one of them. We have another observation of a multi-wavelength field, and we have another observation of the Galactic Center. So I'm going to leave this image up, and I invite any questions, and please feel free to email me if you have any further questions. Thank you.
Thank you, Bradley. That was a great introduction to Meerkat. Any questions or comments for Bradley? All right. Well, thank you again.
Comment, it's amazing work. It's really fabulous.
I just would like to comment that we've been following the collaboration between the astronomers in South Africa and the US. And it's really exciting what's going on and how many publications are coming out.
Yeah, so I think it is. I think there's this real desire to push as much science out as possible, given that when the SKA eventually appears, we won't have too much control over this wonderful telescope, which is really over-designed and performs better than spec. So what we're trying to do is jam as much science as possible before the SKA integration happens, and to basically just increase our science footprint as much as possible.
Okay, anything else, Heidi?
Oh, I was just going to say that this is an amazing opportunity for us to perfect the networking as best we can to ensure the data transfers. And thanks to David Halstead for putting us in touch with one of his people.
Yeah, for sure.
I did want to comment that there was, maybe it's historical, to put it mildly, a reticence from NSF to fund participation with particularly SKA, and this is back in the days of survey plus low, as well as Meerkat into the mid. Has that changed? Is NSF now committed to access, especially there was a pay-to-play model of getting access to the data? My information has gone strangely quiet over the last 2 or 3 years, probably because of lack of travel to conferences. But briefly, Bradley, are you seeing NSF institutions signing up for buying into data access?
So I don't think that the NSF, so I remember that sort of legacy of the NSF reluctance to get involved with the SKA. I don't think that's changed. I don't think it's changed for any other reason, but because the decadal review is already like really full of projects, and it's I don't think that is necessarily an issue that people were reluctant anymore, but just that the portfolio just grew to include the entire available budget. As an aside, we do have active collaborations with people at the in Socorro at the NRAO, and many of these projects are actually led by guys from the NRAO. And so one of the big headaches for us has been to actually ship this data over to people like Bill Cotton. Bill has helped us tremendously in terms of commissioning our imaging pipeline. That X-shaped galaxy has an insane dynamic range. So it's very much a collaboration that, although it's not SKA focused, is something that we would very much like to promote.
Yeah, and to be clear, our director has made it very clear that SKA has to succeed for radio astronomy to proceed. NGVLA, next generation, that's in its own bucket, but one touch point clearly is the scientists. The other one is the data processing. You mentioned CASA. Just FYI, Brian Glendenning has retired now, but you should really touch base with Jeff Kern. You probably know he was the software lead for CASA.
Yeah.
So, definitely make that contact. The CASA software is really written as a general access. We've now got web-based viewers, et cetera, so there's really synergy for the community there. Okay, very good, very
absolutely. Thanks, David.
Great. Bradley, thank you again, and also thank you for staying up late to join us.
It's a pleasure. I just had supper when you guys were having coffee, so that's fine.
Okay, we'll keep that in mind for 2023. Okay, well, we don't have a speaker for next generation EHT. Unfortunately, Greg is out sick. So Mike Nolta, CCAT. Mike is here.
Yeah, can you see my slides?
Yes.
Okay, great. Okay, thanks everybody. So I'm just going to give you a brief update on the Fred Young Submillimeter Telescope, FEAST, formerly CCAT Prime. Fred Young's a major donor. He's given us tens of millions of dollars at this point. So we recently renamed the telescope in honor of him. And so I'm Mike Nolta. I'm the FEAST software lead, and I'm at the University of Toronto. Okay, so just a little background on who we are. Unfortunately, I don't have a collaboration photo. Our first meeting was scheduled for April 2020, but it's primarily led out of Cornell University. And they're also building one of the first light instruments, PrimeCam. And then there's a German consortium led out of the University of Cologne. They're building one of the next first light instrument as well, so called CHI. And then there's the Canadian involvement. So we're heading the software, that's my part, but we're also building one of the camera modules for PCAM, the 850 gigahertz module. And then, of course, our Chilean collaborators at Universidad de Chile, UCSC, and PUC. Okay, so we are building a submillimeter telescope and the highest throughput submillimeter telescope. So we're going to be covering lots of sky. at high resolution. So frequency range is around 200 to 850 gigahertz. We're going to have 6 meter diameter mirrors in a cross-diagonal design off axis. So high surface accuracy, large field of view, very precise pointing. And so we're located on Cerro Chajna Tor, so right by Alma. And this is the best site for 350 gigahertz, 350 micron in the world, nearly twice as good as the South Pole or the Plateau. And we expect first light mid-2024, fingers crossed, if pandemic doesn't get worse. And just a little preview for this group, we're expecting to take about 3 to 8 terabytes of data, of raw data per day. Okay, so here's a photo of the site with a computer rendering of the telescope and some of our operations trailers overlaid on top of it. And just a little close up. This is obviously, you've seen this from Simone's presentation and also a little bit from CMBS4. We're all kind of building the same telescope. Ours is slightly different because we do have more precise pointing requirements. So for instance, this elevation housing, that box in the center that rotates up and down, for us, that's going to be made out of Invar instead of just normal steel to keep the thermal expansion under control. But otherwise, going to be very similar to the SO design. And here's a cross section. So this, can you see my mouse?
Yes.
Good. So anyway, so this I mentioned we have 6 meter diameter mirrors. There's one here and one here. So light comes in through the top, bounces off this one, and then into the primary instrument space here. And then we also have a secondary instrument space down here. There'll be some pick-off mirrors that rotate in when we're observing with this instrument. And then in the bottom, we've got some computer racks for electron here, and then some helium compressors in this process space over here. So I mentioned we've got a couple of first-light instruments. One of them is called CHI. This is being built out of the University of Cologne, and it's a multi-pixel heterodyne spectrometer. So it's going to be observing in 2 frequency bands, one at about 455 to 495 gigahertz, the other at 800 to 820. Each is going to have 128 pixels, and angular resolution here is going to be 26 to 15 arc seconds for the 2 bands. And then, as I mentioned, it's spectrometer, so the spectral resolution is going to be 0.06 or 0.04 kilometers per second. And this is going to be used for, C1, N2, CO line mapping. And so they're primarily going after galactic ecology. So they're going to do this so-called Gecko Survey, which is going to be looking at the galactic midplane, nearby molecular clouds outside of the plane, and Magellan clouds and nearby galaxies. And so they're going after the structure formation, the structure of molecular clouds, star formation, and the chemistry and the microphysics of the interstellar medium. I saw somebody raise their hand. Was that, did somebody have a question? Okay. Okay, and so the other first light instrument is PrimeCam. It's, you can see the cryostat here, and it's going to have 7 optics tube. That's these hexagonal components here. And each of these is going to have a field of view of about 1.3 degrees. So it's going to be cooled to about 100 millikelvin. And this is about almost 2 diameters across. Sorry, 2 meters in diameter. So 5 of these modules are going to be broadband polarimeter cameras between 220 and 850 gigahertz. with beam sizes of between 59 to 15 arc seconds per pixel, and a number of pixels between 7 to 20,000 per module. So in total, will be about 60,000 pixels. And then there'll also be 2 spectrometers, 220 and between 220 and 410 gigahertz, and the beam size of between 58 and 33 arc seconds. And these will have about 6,000 pixels each. And the science goals here are several. We've got going after the first stars, so the epoch of reionization, tracing galaxy evolution, characterizing CMB foregrounds. So we're going to be observing at much higher frequencies than SO or CMBS4. And so that 850 gigahertz camera will really come in handy in cleaning some of this stuff out. Galactic magnetic fields, galaxy clusters, so SE, so through the SE effect, Rayleigh scattering, and time domain phenomena. And so this is just a little map of the survey, some of the survey fields we're going to be observing. So this kind of shaded region here is almost half the sky, and that's our wide field survey. So it's covering much of the same ground as Simon's and the other projects on this call. And then we have a few deep fields for spectrographic, deep fields for spectrometry, and then some targeted fields for galaxy evolution, these so-called stripe 82 and gamma 15, that sort of thing. Okay, so those are our 2 first light instruments. Unfortunately, PCAM has been a bit delayed, first with COVID, and now apparently the vendor, we've been told by the vendor that we're being bumped for defense work. So we have a backup plan, which is a scaled down called ModCam, which is a scaled down version of PriCam. So this is a cryostat that holds just a single optics tube. And it's undergone its first cool down. And if PrimeCam is not ready on time, then the plan is to ship this one with the 280 gigahertz module for the first year. And then PrimeCam will ship most likely a year later. Okay, so we are at extreme altitude. So we're on the eastern slope of Cerro Chajnantor near Alma, and just down slightly from Tau at 5,600 meters. We're up here because we really want, we need to get the PWV as low as possible. We're up at very high frequencies, 850 gigahertz. And at our site, the PWV is about, on normal days, 36% lower, but it can get up down to almost 80% lower when the inversion layer drops below us. And we're, as I've mentioned before, we're twice as good as the plateau or South Pole at 350 microns, 850 gigahertz. But the other way to mention that is that there's a legal change at 5,500 meters. There's much, the regulations are much tougher once you pass this threshold. So you require extra medical tests. Everyone has to be cleared, has to have an actual hypobaria test before they're allowed to go to the site. And Surimi has to approve every contractor and every company, and they receive reports on every individual worker working at the site. And so because of this, fuel companies won't make regular deliveries to our site, given the altitude and also the road. So because of this, we're going to need trench power. We're going to need to site our power at a lower altitude and trench power cables and fiber cables down the mountain. So here's just a close-up of the road. So we're right here. Tau is another telescope that's going to be right at the summit of Cerro Chajnantor. And then down here is the Alma Road, and Alma Pad 409 is down here. So our road is in orange and red. You see it's a bit twisty. And the plan is to put our generators right here at the so-called service area. And then we will trench power and fiber from the service area. We'll take this shortcut, this yellow dotted line, and then up the road to the 2 telescopes. And then we're also going to trench fiber from the service area to pad 409. And then at pad 409, we will connect to 2 of ALMA's dark fibers. And we have an agreement with ALMA, and they very kindly allowed us to use 2 of their fibers. So yeah, so like I said, we're trenching power, so it makes sense to trench fiber at the same time. I mean, the original plan was to send disk packs. Thankfully, we won't have to do that. So we have an agreement with ALMA. They gave us some land for that service area for our generators. They've also, as I said, they're gonna lend us 2 of their dark fibers, starting at pad 409 and then connecting to the AOS. And then at the AOS, we'll connect to Ryuna's point of presence. And then, yeah, so in terms of data transport, you know, we're going to have 2 modes, you know, whether Chai's observing or whether PCAM's observing. And so when Chai's observing, we're going to be shipping the data to Cologne in Germany. And if, you know, at a 24, and the average rate over 24-hour is going to have to be at least 685 megabits per second to enable us to get all the data to Cologne within a 24-hour period. This is actually, you know, the burst, we're actually taking data twice as fast as this, but only at night. And so averaged over 24 hours, it'll be almost about 700. And then we'll also have a small, you know, a low bandwidth connection to Toronto just for housekeeping data. And then when PCAM's observing, the data is going to be shipped to Cornell. It's about half, you know, it's not quite the same data rate as Chai. So this is now estimated to be about 400 megabits per second. And so, yeah, so we've done some preliminary network tests with, thanks to Ryuna's help, between the AOS and Toronto. So Sergio and Albert from Ryuna helped us out. And over a matter of a few days, we ran some iPerf3 tests between the AOS and SciNet, which is here in Toronto. This is one of Canada's largest supercomputer centers, and the plan where we're going to host at least the housekeeping data, and we're trying to get funding to host the entire data set as well, but that hasn't come through yet. So yeah, so there was basically a laptop connected with a 1 gig connection at the AOS, and we've essentially maxed out that link. Except in one direction. So sending UDP back from SciNet to the AOS. Apparently that's a higher packet loss, which is slightly unusual. Usually you'd expect the TCP to also be affected. But anyway, we're not quite as interested in this direction because we're going to be shipping data outbound and not downloading it to Chile. And yeah, then I'll just close with some pictures. So I showed these. I think I showed these last year. The summit has been. The summit had been leveled just before my talk last year, and the foundation has been dug. And then, unfortunately, the COVID shut us down for pretty much a year. But the picture on the right is they have resumed the work at the summit. And the first thing we had to do was to clean up the hole. It kind of degraded a bit. On the year everything was shut down. So this is the hole this foundation is going to go in. And here is, because I think Simone alluded to this, it's hard to pour concrete at these elevations. So what we're doing is most of it is precast, and that's sitting in I think that's Kalama, waiting to be installed. And then the figure on the diagram on the right, the bits in green are going to be the concrete that we pour at the summit. And so it's going to, fill in, kind of grouch in the gaps here, and then also hold the bolt ring that the telescope sits on. And yeah, and I mentioned, so we're going to be trenching power and fiber. That has begun. The total length is about 9 kilometers from the summit to pad 409. We're about 20% of the way. We're 20% complete at this point in terms of digging the trench. And then the first reels of power and fiber have been installed, and that's what you can see on the left. So I guess under Chilean law, you have to put these bricks on top of the cables. And we expect this to be done by July. So that'll be power and fiber all the way from pad 409 to the summit. And the telescope is under construction in Germany. They've gotten some of the first pieces. So they're going to build it entirely in Germany before shipping. And so we've got the first pieces installed. So we've got the support ring here, and then the middle of this, the so-called yoke traverse. So this first floor. And so that's sitting on the foundation. And yeah, and then it'll be constructed over the rest of the year. So yeah, so by November, the whole telescope should be constructed in Germany. It should then be disassembled and shipped to Chile in Q2 next year, with final acceptance in Q1 of 2024. And the instruments will ship at the end of 2023. Chai and likely ModCam. PrimeCam will likely be delayed until 2024. And then, yeah, fingers crossed, science observations should start late Q3 2024. And with that, I'm done. Then just as, note of thanks, like, as I mentioned, our original plan was to ship discs, but thanks to the efforts of the people on this call, we won't have to do that. So thanks again.
That's great. That's great. Any questions for Mike?
I don't have a question, but a comment. Great talk, Mike. It's really nice to see this progress with CCAT. I will confess to tromping around on Cerro Negro in the late 1990s with Riccardo Giovanelli when some version of this project had begun. So seeing the progress is really great. Do you care to tell us who the vendor of PrimeCam is?
It's Vertex.
Oh, okay, thanks.
I do have a question for you, Mike, on the map that you showed with the summit. You showed the path of the of the fiber.
Yeah.
Yeah, that one right there. And so that will be your primary path.
Mm-hmm. This is our only
Okay.
path. Yeah.
Okay, because I also heard you describe the connection to Alma and to Reuna. Is that going to be a backup path?
Okay. So this is the part that we're building in this diagram. And then, yeah, and then here at pad 409, we interface with the pre-existing Alma dark fiber to the AOS. And then at the AOS, we hook into Reuna's point of presence.
Okay, so you do have a different path in the event you have some event with your fiber that gets cut or you have any problems.
Well, no, this is our only path. Yeah, if it gets cut, we don't have. There was, originally we were going to have try to do a microwave link.
Yeah.
But it's complicated because we don't have line of sight because we're to San Pedro, so we would have to have at least 2 links, and then it's also also complicated because of Alma's frequency restrictions on this side of the mountain.
I see. Okay.
So yeah,
Okay.
so if we're going to plan to have a buffer, disk buffer at the site for exactly this contingency. So
Gotcha. Okay.
several weeks, if the fiber gets cut.
Okay. All right. We have some hands up from David and Christian. David, do you want to go first?
Probably Christian should go first because he's probably going to say what I'm thinking.
All right, Christian.
I don't know. So it's not really a network question, Mike. I was wondering what kind of precautions are you taking for the lower ring in case of earthquakes?
I mean, that is something that went into the design. We have an earthquake spec. I don't remember it off the top of my head, but yeah, apparently that's been baked in. I'm sorry, that's not a great answer.
That's fine. Thank you.
Mine was a bit related. I thought that the Telefonica Silica link actually went through the high site over to the gas pipeline. So, the link goes up the hill to get out. Is that correct?
No. So this is this. So yeah, this is the diagram is the one that we're building ourselves. So the orange, then the red, and the yellow. So we're the ones trenching and paying for this. After that, I'm not entirely sure where where everything goes.
Yeah, but for Ulmer, I believe that the fiber link from the OSF goes back up the hill to get to Antofagasta and down to Santiago. I don't think it changes anything, but just FYI, the Ulmer link doesn't do what you'd expect and goes out through the road. It goes up the hill to get out.
Oh, I'm kind of just taking it for granted. Once we get to pad 409, it's like, well, that's somebody else's problem. So.
No doubt.
Right.
But as we look at redundancy and availability, yeah, there's a bit of reality that the fiber running over the hills was intended to go through the high site following this right away of the gas pipeline that never actually got used, but it was a right of way. So there's history on any fiber optic pole.
Yeah, redundancy would be great, but this trench alone is costing us $3 million. So it's
yeah, you're doing good with it. It's always a matter of how many other people want to use this trench, and last thing you want to do is pull your own, but it is what it is. And the number of washouts and things over the last decade from the highest, driest place in the world has been remarkable.
Yeah, it's the driest, and then the weather. There's no data, and it's because it snowed. Yeah, no, I mean it'll be an excellent question. I mean, how robust is this going to be? I mean, how many cuts are we going to have? How reliable? Only way is to try, I suppose.
Well, there is another wrinkle that the new ALMA correlator will probably not be at the high site. It will probably be down at the OSF.
Mm-hmm.
So, having to run all the 66 dishes or 50 dishes for the larger dishes back down the hill to 7,000 feet is maybe on the horizon, so that the need for fiber will endure.
I think we already kind of ran into that, because I think originally we were supposed to get like four fibers, and then that got cut to 2. Yeah.
Never pull enough fiber.
I mean, true confessions, Ruben doesn't have a backup to get down the mountain into the valley either. I mean, that occasionally is an issue with ice and buildup on our line-based fiber.
Did you bury yours, or?
No, unfortunately, it hasn't been buried yet. It's something to think about in the future. It's on poles, and occasionally they get loaded. We actually had an event a few years ago where the poles collapsed due to ice load, but the fiber did not get cut.
Yeah, I could add just a couple of comments on that. If this is Jeff Cantor, what we found is that there are frequent cuts wherever we have Rubin fibers running through populated areas. And in fact, in some areas, we've had cuts related to people mistakenly thinking there's copper in those wires and trying to steal the copper. So the problems we've had on our own properties have more been weather related, as Bob pointed out. And in spite of that, we through a series of improvements to ours are on poles. Through a series of improvements to the poles, we've managed to avoid repeats of that incident that Bob referred to, where the poles went down. So if you're underground, obviously you're not going to have that same issue. We do have had occasions where we've had rodents getting into boxes where the fibers are and wanting to eat the plastic coating on the fibers. So we've done a lot of mitigation to make sure the boxes were sealed and so on. But you will have some kind of issue at some point, no doubt. I guess
Sure,
is the bottom line.
Yeah, I'd definitely be interested to hear more about the rodent experience. Yeah, because I think we're going to have every half kilometer the boxes.
Yeah, we actually put foam to keep them from running down through the conduits from box to box. So there's a number of little mitigation steps that were taken. We also had parrots perching on wires that were on the poles, and had to take mitigation steps to put these little rollers around the wires near the poles, so that when the parrots tried to perch on them, they'd roll off, because they're an endangered species, and we had to work with the university there and so on. So there's lots of interesting little tidbits.
Just to be clear, to add what Jeff said, and thanks, Jeff, for all that. We do have a backup on the areas where we've experienced the outages in the main line, and that our backup and redundancy is quite robust, and now basically, at least now before we started, the full survey is completely almost transparent to what's happening on the main line if it does get a cut.
Yeah, once it goes to the main lines in the La Serena area, then we're fully redundant from that point out all the way to the US.
Yeah, one more thing that usually happens in public places with fibers. For some reason, people like to shut to the fibers. So that's also one of the problems that we had. But as Bob said, having the two path is absolutely critical. If you're going
that happens all over the world, unfortunately. We see that in the rural United States too.
Yep.
Mike, could you please take your slide down? And I'd like to ask everyone to turn on their cameras while we continue talking, so I can do a screen grab. I see David has a question. Thanks. David, you could ask. We don't have to be quiet while I take pictures.
No, I just wanted to recite some poetry while I figured out how to turn my hand down.
All right, well, just bear with me then. I'm gonna take a picture or two.
All right, well,
now.
I'll go ahead and then continue on. I think our next speaker is going to be Sam Chan for Sam, you there?
I am here.
Yes. Okay, great. So since we don't have Marie to give an update on US ELT, Sam has offered to use that slot and give us an update on I'm sorry, what's the name of your project, Sam? I'm sorry.
We're Giant Magellan Telescope. So we are part of
GMT.
Yeah, we're part of the US ELT.
Yeah, all right, great. So hold off until Heidi's finished.
Go right ahead. I grabbed a few. If I
Okay,
need
great.
more, I'll let you know. Thank you.
Thanks, Heidi. All right, Sam,
All right, so let me see.
go right ahead.
Which screen that's. Is this the right screen to share? Actually,
Looks good.
Let me move this over, right? Okay. So I'm Sam Chan. I'm the IT director for Giant Magellan Telescope. Full disclosure, I am not a scientist. I am strictly IT. I handle all the corporate, the information stuff, all the security, all the firewall, the transport. Once the data is ready, we transport links and things like that. That's my department. I don't engage in, the build, the structures, or the installation of the actual telescope device itself. All right. So Giant Magellan Telescope is part, so I just threw this thing up last minute, is part of the US ELT program. So Marie was gonna do the presentation today, but she is sick. So I put this up. So we are one of the two. The US ELT is the United States Extremely Large Telescope. So there's a GMT, and then there's the TMT, right? That's the two telescope that is in the process of being built. Ours is scheduled to come online, I believe, 2028. It keeps on being pushed a little from time to time, either fundings, NSF fundings, or pandemic like everybody else. I put the NOAA lab there is because I think once we start getting the NSF fundings, I think NOAA lab would have a lot of control over what we do. I think I've talked with them. It may be possible that all our public data will be transferred there to NOAA lab, and then they will put it up for public consumption. But we'll have the copy of the original data on in our facility as well. That is to be determined at the moment, but it looks like that's where we are heading. A little bit about GMT for the new folks. GMT is composed of a consortium of leading university and research. So we have a lot of university that are partners. But we also have people from international as well, from Australia and South Korea. I thought we had Japan in here also, but I don't see them on the list. We got the Weizmann Institute of Science. I think 2021, they joined our partnerships. So these are all our partners. And I guess the next new partner would be hopefully the NSF. That will give us more fundings. This is an eye chart, but the bottom one is what I wanted to show, that the size of our telescopes basically has a resolution or resolving power 10 times the current of the Hubble telescopes. Of course, it's a different location. One's in space, one's on land. So we are located at the Las Campanas area. We are next to the Magellan Telescope. Actually, it's called Las Campanas Observatories. They own the site. We lease the land from them, and we work with them. So most of our infrastructure, actually all our infrastructure right now, run through LCO observatories. It goes down to La Serena, it comes up here, and that's what we use this at the moment. We don't have an independent fibers going down the mountain. There is talked about trenching a power line going down the mountain, a different path than the current power line coming through. I'm hoping when they do, we at least put 24 strands down that power line, and then maybe extend it somewhere else, either to Newell Lab or to the Vera Rubin observatories, or just get it to the, I think our base facility will be in El Pino. That's what, so it hasn't been confirmed, but I think that's where it is. So we'll probably have to link stuff down there, and then from there either go to the Vera Rubin observatories or to the Newell Lab, well, whichever one the data is supposed to go to. Have not been told. Also have heard that in terms of Newell Lab, maybe they want to put the data at inside AWS. We have not confirmed, but either way, whether it's in a data center or at AWS, we still need a transport mechanism to get us there, right? 'Cause I think right now the fiber that's coming up, I think the guys, Albert, I think Rayona is control of that mechanism, right, from all the way from La Serena up to the mountain. Here is the little rendering. I think this is the current rendering as of 2021. So there are many different renderings of the telescopes and the enclosures, but this is the one that they have currently. This is where we are. So again, the driest area and has happened to have snowed in October 2021. So we took a picture of that. So I thought we put it over here, that there was snow on that mountain. So to the left is where the telescope will be. We actually excavated the spot, but we haven't done much after that. We've managed to build the water tower, water equipment buildings. So at least we got water into the facility. As a comparison in terms of size, this picture is I might have showed this before in different years. So this is what the GMTO looked like. The picture in the middle there is the James Webb Telescope, the size of the James Webb telescopes. So that is the comparison of the size of the telescope that we're building. And another, so somewhat at odds of the of what we're building, right? So my explanation is we're building something that's almost 50 meter tall, and we have to rotate it in every which way. The mirror itself is, each mirror is 20 tons, and there are 7 of them, on a platform that we need to rotate in every direction. And to make it simple, put that into about a 22-story building and rotate that building. Right. So I don't know, a lot of people on here may not know about the Rose Bowl. The Rose Bowl sits 100,000 people. So this is an image, a rendering of what it would look like if we drop the telescope into the Rose Bowl. Yeah, that's what, it's what it would look like. So the other part, a lot of our data, surprisingly, scientific data is a lot, but a lot of our data comes from all these environmental data, the mechanical data. Like this is the actuator, the support mechanism to hold one of the mirrors, right? So, if you look at all the cables, all the fibers, all the stuff that runs, so we actually record all these data as well once it goes online, and that will be part of our environmental telemetry data. Supposed to record everything. We also are beginning to start the secondary mirror. So the telescope the primary is at the bottom, and then it reflects to the secondary mirror, and then it reflects back down. So we're in the process of starting the secondary mirror. Let's see. So all the giant mirrors. So most of them is in. We've already completed most of it. Not completed. The first 2 are completed and in storage. 3, 4, and 5 are in production queue, and number 6, I was there 2 weeks ago. They are into the casting process. Each of them takes about 3 years in the process from casting to complete. And this is, this is where I forgot which segment this is. It was in the cast and it's pulled out. So here's where the projected data is for the GMT, at least. The 10 to 40 is the total data. That's all the including the non-scientific data. I think the scientific data itself is much less, maybe only about 10% as much. Again, we don't expect to see our first light at the moment, about 2028. So, well, and also our construction has been delayed a little, so we're waiting on the NSF funding to continue the process. So right now we are in somewhat operation, not operation, but support mode, right? While we're getting some more funding in order to continue with the build. But once the build is done, like I said, my goal is to leverage what is already in existence, if possible. So, but we'll either get the data to the US, into the NOAA lab in Tucson, or we'll get some to the cloud somewhere. I don't plan on building a data center to store all of our data besides either the one at the summit, or we may bring it down to Alpino, right? Depending on what they say, whether it's okay to keep it at the summit or at Alpino. I have not been told, but either way, once that is done, we just have to move the data to those locations. So right now, our corporate office is still in Pasadena. We are in the process of relocating from our Pasadena office to another office in Pasadena. So I am, because of the short time frames, I am looking to see, this is a side, maybe to put it in our data center in a co-location instead of building out a data center in our Pasadena office for 5-year operation, right? Because I think once we are completed, I think all the operation will move to Chile. I don't know how big of an office will be in Pasadena. So I'm iffy on building a new data center in a new location in our new office. So as of right now, all of our operations is in Pasadena. We replicate all the data to the summit so that the summit is basically has the same data, the same services as Pasadena have, and we also replicate it to the cloud in terms of data. That way, I guess, well, we've tested it so that if Pasadena goes away, then we just bring the equipment on the summit online. Now the summit, the reason we have a lot of power issue in Chile, so we have not resolved all the power issue, all the frequency issues in the powers, and our power team is not in a hurry to resolve, as the facts that we are a long way from operation. So I would rather put our data center at the summit, but being that we have a power issue, we just leave it as a backup site for now. And I think that's it. That was my quick presentation for this meetings. As there's not a lot that are happening at our site at the moment. We are just waiting for fundings, things like that. So, but I am talking to the folks that are involved to see what is possible, what is out there. Hopefully in what, 6 years when we come online. So there are different technologies that we can leverage. That's all I have.
Thank you, Sam, for stepping in. It was a really good presentation. And I especially like the image of the Rose Bowl with the telescope inside. Do we have any questions? Oh, okay. There's a request in the chat from Vasi to please make sure you upload your presentations to our Dropbox. So if you haven't done that, please do it. And we have open discussion now. Is everybody satisfied or comments? Bob, you want to sum up anything, or Julio? No.
No, and just
long day, huh?
the talks have been excellent, and I just want to thank everybody for the reporting that they've done, providing updates on where the projects are, and so I really appreciate everybody taking the time to do that today. Tomorrow, the network operators will be reporting on their networks and progress since the 2021 SAC meeting. So please join us tomorrow as well, so you can learn more about new technologies, new activities with the networks that are supporting your projects. I really encourage you to engage with us and attend tomorrow's session as well. Okay, so with that said, we're finishing. Well, it's more or less on time. I guess a little bit early. Unfortunately, we had two people that reported sick, and so hopefully we'll get their slides and make them available for you all and include them in the 2022 report. So there are some comments that just came in from Jeff. Jeff, do you have something you want to comment?
Sorry, I was actually replying to Bob Blum's question. His question was in chat to me, and I inadvertently sent it to everyone. But
Okay.
Since I did send it to everyone, I was just about to say, correct me if I'm wrong. The question was, what are ESO's paths out to Europe from there? And I believe we have a traditional path that went up through some East Coast RENs in the United States. And then also they've opened up the Bella cable now.
Right. I see Albert. Albert might be able to respond to that better than me.
No, that is entirely correct. Since the Bella cable was released, we have already set up the new path over the new cable. So this is the primary link at the moment to reach the institutions of Europe from Chile.
Okay. So Albert, maybe you can say a little bit more about that tomorrow, if it makes sense, or you get asked the question as well again tomorrow.
Sure, absolutely.
Okay. All right. I guess with that, I'll adjourn the meeting today and thank everybody again. And we will see you tomorrow at 11 a.m. Eastern Time. Enjoy the rest of your day and evening. Thank you.
Bye-bye.
Thank you all. Bye-bye.
Bye-bye.
Bye.